Problem number 1 is a huge solenoid, one that is used for nuclear magnetic resonance. It has a cross-sectional radius, circular radius, 0.5 meters. It has a huge length of 2.5 meters so that the whole body can go in there. It's used for medical purposes, and the magnetic field is quite strong, is half a Tesla. It's a huge machine. And the first question is, how much energy is stored in that machine? Well, the magnetic energy per cubic meter, joules per cubic meter, is given by this relationship. You have seen this several times. So if I multiply this by the volume of the solenoid, then I should get the total energy. Of course, I've made the assumption then, which is an approximation, that the magnetic field is constant in the solenoid, is zero outside, and is also zero outside near the ends of the solenoid, which we know is not true. But it's a reasonable approximation. So the volume then equals pi r squared, which is the cross-section through the solenoid, and the length equals L. And I put in the numbers, and I find very roughly 2 times 10 to the 6 joules. But this you should consider as a somewhat rough answer. How much current goes around a ring which has a width of 1 centimeter? Well, we will have to revisit the solenoid and go back to some earlier calculations that we have made to refresh your memory. Let's suppose this solenoid has length L and it has n windings, and the current through each winding is I, and we don't know either one of them. But we make the assumption, perhaps a little bit naive, that the magnetic field only exists inside the solenoid and that it is constant and that it is this 1/2 ampere. Not ampere, 1/2 Tesla. I now use Ampere's law to calculate this magnetic field in a way that you have seen many times. I take a closed loop, let this length be y and let this length be y. This is very far away. I assume the magnetic field is always in this direction. And so when I calculate the dot product from Ampere's law, integral b dot dl, I only have a contribution through this part, because B is perpendicular here to dl inside the solenoid. It's also perpendicular to dl here. And here the magnetic field is very weak, and certainly when we take this very far out, the contribution is approximately 0. So I would only get then, if I go around this closed loop circle in this direction, I would get only B times Y. That now equals I through this open surface. Mu0 times I through plus mu0 times the displacement current. Don't confuse this with DC, this is displacement current, and there is no displacement current. So now comes the question, how many times does this I go through this surface? It penetrates through this surface many times, and so we get B times Y equals mu0. Y divided by L times N is the number of times that it penetrates through this surface at these locations times I. And so I find that IN equals B times L divided by mu0. You realize, of course, that the Y cancels. And if you wanted the equation in terms of B, well, then you would have mu0 times N times I divided by L. This, by the way, would mean, just to give you some feeling for it, that if, I'm not saying that's the case, but if I were 100 amperes, then it would mean that N would be very roughly 10 to the 4 windings, because when I calculate IN, I know B, I know L, and I know mu0, I find very roughly 10 to the 6 amperes. So that's the meaning of IN, the way I have derived it. Now I'm going to look at this cylinder, not as individual windings and individual windings, but I'm going to look at it literally as a shell cylinder, open here, and it has length L, and there is here this combined current going through all these N wires, going around and around and around, making this magnetic field like so. And suppose I took a knife and I cut through here. Well, I really don't want to cut, but I want to have a surface here that cuts here through all these currents that go through here n times. What then is the total current that goes through that sheet? Well, that of course is 10 to the 6 amperes. I just calculated that. But now, I don't take a length L, but I take something more modest. I take a ring of which this is only 1 centimeter. And now I want to calculate how much current goes through that 1 centimeter. So it's immediately obvious that it is the 10 to the 6 amperes divided by 250, and that is 4 times 10 to the 3 amperes, going only through this ring, which has a thickness of 1 centimeter. Professor Bertschinger is now asking you, what is the outside force onto this 1 centimeter ring? Well, I would like to make a picture from above. So this is this ring. It has a thickness 1 centimeter going into the paper. It has a current going in this direction. And the magnetic field, which we have assumed was pointing upwards, is inside B. It is this half Tesla B field. Now we know that dF equals I times dl cross B. Here's a cross product. And so if I take here a little element dl, always in the direction of the current, then you can check for yourself that dl cross B is a force that is pointing outwards. It's a little force dF. And that force will be radially pointing outwards everywhere. dF, dF. And this radius then being little r. And so even though the net force on this ring is 0, because all these forces of course average out to be 0, I'm sure that Professor Bertschinger had in mind that he wanted you to integrate over the circumference 2 pi r the force sort of like this. I don't quite know how to express it. I would have phrased it slightly differently, but I think his intentions are quite clear. And so, what that would mean then, that the total force, if you add up all those radially forces outwards, would be I, which is in this ribbon of 1 centimeter, times 2 pi r, which is the circumference, times B. That's this B, because the cross product, you can forget the cross because the I and B are at 90 degrees angles with respect to each other. Now we know that this value is 4 times 10 to the third. We know 2 pi r and B. And what do you find? You find 6,280 newtons. That's what you find. This value, however, is definitely too high, because I have assumed now that the individual windings of the solenoid are all completely immersed in that field of half Tesla. And that's not the case, because outside the solenoid, to a reasonable approximation, the magnetic field is 0. And inside the solenoid, it is half Tesla. So it is more reasonable, as is suggested by Professor Bertschinger, to choose for a mean magnetic field half the value of the field inside. So instead of half Tesla, we should take 1/4 Tesla. And therefore, the actual force that you would experience then is this value divided by 2. This is the sum then of all these forces as they are pointing outwards. A more reasonable question is, what is the pressure on this ring? Now pressure equals the force divided by the area. The force is now 3,140 newtons, half of 6,280, and I must multiply that by 2 pi r, the circumference of the ring, and the ring has a height of 1 centimeter. I work in MKS units, and I find 10 to the 5 newtons per square meter, which is 1 atmosphere. This is an overpressure. Clearly, the air pressure outside and inside the solenoid are the same, it's 1 atmosphere. But now, as a result of this current and this magnetic field, which is produced by the current, there is an overpressure over and above the equilibrium, 1 atmosphere in and 1 atmosphere out, which is trying to blow this magnet apart. 1 atmosphere is quite a pressure. There is 1 atmosphere pressure on your hand, which is 10 newtons for every square centimeter, or I like to think in kilogram forces, 1 kilogram force for every square centimeter. Why don't you implode? Well, because there is equilibrium. Inside your body, the pressure is also 1 atmosphere, so you do not implode. But if you take a metal can and you close it properly and you suck out the air, then the metal can will implode, as you have seen last year during a wonderful demonstration in 801. Now, the outside force, the 1 kilogram per square centimeter, is not compensated by a similar pressure from inside because you're sucking the air out. So this atmospheric pressure can sometimes be very, very noticeable. In the case of the magnet will experience an overpressure from inside out of 1 atmosphere. And now you're being asked, or you're being told, that the magnetic energy density, which has as dimensions joules per square meter, a joule is a Newton meter per cubic meter, so a joule is also newtons per square meter, that this has the same dimension as that. And if you do calculate 1/2 b squared divided by mu 0, which in this case is easy, because B is constant in the solenoid. If B is not constant, it's a little harder. And you put in the numbers for B and for mu 0, what do you find? Lo and behold, you find the same 2.5, 10 to the power 5. So again, you find the same 1 atmosphere. So in this case, the magnetic energy density is exactly the same as the overpressure that the solenoid will experience.